Have you ever wondered how a distributed database works? What the cap theorem is, why you need to partition data, why you need to scale to multiple nodes? It all has to do actually with kind of the laws of physics and how you can model data in a distributed fashion. Today, I have expert Mark Brown from Microsoft here.
Hey, Adam. Thanks for having me on.
Yeah, I'm pretty excited because I have this. I grew up on relational databases and I was pretty good with them. I actually spent a lot of time with SQL Server. I know you're from Microsoft. I love that database. But now we're in a new world and sometimes you have problems, where you need a distributed solution, where you need replication or you need certain times of uptime that just aren't possible. And yeah, I just don't understand that world. So I need your help.
That's why I started in the same place. I started using, well, it was Sybase back then. It was actually, just to give you an idea how old I am, back in the 90s, there was Sybase first and then that SQL. And I did the SQL for a lot of years as well, did lots of stored procs and just used relational databases like everyone. And here's the thing, like relational databases are great, right? And they're everywhere, but there's limitations to what relational databases can do. There's typically kind of a storage limitation for how much you can stick on a single node before you start to shard. It's typically what the maximum size for like a VM can store. So you're into the, many hundreds of terabytes or whatever the max, but it's not terribly large. And so beyond that, you have to start sharding, right? And that's kind of one of the main design patterns for a database like Cosmos is it's by default designed to scale out, right? Like relational databases scale up and down, right? You just change the size of the VM and the storage size remains the same. Or, well, I mean, you can change it, but only up to a point. And then the other thing too is relational databases are not distributed typically in a geographic fashion, right? Or
Yeah.
they don't also have kind of redundancy at these other different levels as well. And that was kind of another aspect of this service. So I wanted to kind of spend some time with you guys and talk about kind of two main areas with Cosmos and just helping you understand, like, why is this database the way it is? When people first use Cosmos, it can really confuse folks as to why it works the way it does, because they try to use it like a relational database and design for it and model data for it in a way like a SQL server would work. And then kind of quickly realize like, it's not designed to work that way. This is not making sense. So I thought if I explained kind of these underlying architectural aspects of this, it would help folks with it. And kind of where I wanted to start with is this scale out nature of the database, right? So when you're dealing with a relational database, you have a database essentially that scales horizontally, right? Like you add compute, you get a bigger VM, you can process more requests, you can do more stuff. That's not fundamentally how Cosmos works. It's actually designed to scale out. So you don't add larger VM sizes to grow kind of its compute. You just keep adding nodes to it, right? And so each of these things is great because they all come with their own storage in there. And we call these partitions in there, but they're fundamentally like a node, if you will. And it's each like its own little computer or it's actually a slice of a VM technically. So they all come with their own storage in there. They also have their own compute. So each of these things has its own CPU, its own memory, its own IOPS in there. So this is nice. You could actually individually address these things. And I'll get into that, how you do that a little bit later. But fundamentally, what you get then with this type of architecture is basically you get infinite scale. Like you could just keep adding nodes to this thing or partitions to it and get more storage, or you can keep adding nodes and partitions to it and just getting additional compute to process additional requests. So these are partitions is what we call them internally. So I wanted to explain kind of a little bit like are these things fundamentally. So when you're writing data into Cosmos, you usually just don't need to care where it's going physically, and we don't want you to care. So we have this concept called a logical partition. And so as you write data into Cosmos, the only thing you should care about are these logical partitions. And the way you address this data into any of the logical partitions is you have this thing called a partition key. Now, this partition key is just a property that's within your JSON document, right? So like a record in in a relational database or a column, we have documents, and we have properties, right? So that's kind of the fundamental equivalency, if you will. But that's kind of where that equivalence ends. So one of those properties is a partition key, and every document needs to have this partition key. And the reason is it acts like an address for where you're going to store this data, right? This logical partition, even though we try to abstract it away, actually drives where it physically sits within, this cluster that where your data is stored within there. So you give it a partition key, and I'm going to use a username here. And then everything you write to it with that username gets routed to a different logical partition, which may sit on a different physical partition or a different place or a location within a cluster within there. So from a logical partition standpoint, the size of these things is 20 gig. Now, people usually have a rather poor reaction to this. They're like, 20 gig? Like, well, wait a minute. You just told me this thing, you can have unlimited size, infinite size or whatever, like within there. And there's a good reason for this. And that is when you have small partition sizes or these small shards within there, you get a greater level kind of elasticity within there. So if you're working with, say, a single instance database, it could be a Mongo or it could be a SQL, it could be anything, basically. If you want to go up to that next size, you generally have to buy a much larger size. And the cost of that can get rather expensive as you get kind of into those upper levels there. The other thing that's key to keep in mind as well is when you step up into those other upper levels, you're paying for storage that you're not using. Whereas with Cosmos, you get it in these 20 gig, actually it's in more 50 gig increments, and I'll show you that in a second. But the more fine-grained it is, the smoother the cost profile is of this. And also the more adaptive, the more elastic is what we call it, the underlying database is, because they're small partition sizes. So you can add or remove them very, very quickly. Also, we relocate or rehome where logical partitions sit behind the scenes all the time as your workloads kind of grow and shrink. And having them at these smaller sizes just makes it easier to co-locate and then relocate these things.
So let me ask you, Mark, like if it's, I literally worked at a place and there was the database server in the back, but like, what is this? Like, is that 20 gigs? What physical infrastructure does it run on? And like, how many of these 20 gig slices are on a physical machine? Or what's under the hood that I couldn't see here?
Right. So within so we have these logical partitions, which, like I said, is the only thing you really know about them is you have a partition key for it, right? So that would be like a username we have in there. And that's the only thing you ever know about them. And the only other thing you can know about them is the max size of these things, 20, can we grow up to 20 gig. Logical partitions, have to sit on something physical. So you have these things called a physical partition, which is basically where these things will reside. Physical partitions can be a maximum of 50 gigs in size. And those are basically the boundaries of the compute. So that thing I was showing you earlier, I keep backing up here until I show you, like one of those things right there.
Yeah.
That's basically, those logical partitions are sitting on what would be a physical partition. So here you can see I've got, on the left-hand side, I've got 2 logical partitions sitting on one. I've got 1 logical partition on another and 3 logical partitions on the third. And how this works is when logical partitions start growing to a particular size, you will have a split for logical partitions, but also we will relocate them as well so they can either co-locate, or we will split them and put them on their own new physical partition, and then essentially grow the physical storage underneath a container, right? Like all this stuff is basically wrapped in what we call a container, which is another logical construct for all this data that sits within there. So that's the idea, is that none of this stuff do you ever have to touch, right? Like you have a container, which is itself a logical construct. It has a name, and that actually sits within a database, which is also a logical construct. But all of this stuff at a physical layer is sitting on these things called partitions, right? And so when you think about kind of the how do you organize these things mentally in your head, you've got these logical constructs. You have an account, and then within it, you have one or more databases. Within a database, you can have one or more containers. Within each container, you can have 1 to an unlimited number of partitions that is driven by this thing called a partition key. right? And within those partitions, you have these logical partitions, which is the amount of data that has that same partition key value. And then those sit on a physical partition, which can host one or more logical partitions within them. Does that make sense? Kind of the resource of the hierarchy, if you will, of the resources within there.
Yeah, yeah, it totally makes sense. And like, I think to me, the thing that comes to mind is like, you could build this yourself. Like, I have before worked at a system where they outgrew the relational database, so they put in like manual kind of sharding, right? Where the connection pooling would actually redirect you based on a key of like customers, right? So you were basically manually taking a relational database and scaling it out that way. And in fact, now there's products, right? Like there's a
Sure.
Postgres
There's
or
Citus there, and then you have things. You have these other NewSQL databases like I think Cockroach and Yugabyte also do a scale out. MySQL, I know Facebook infamously wrote a scale out architecture for MySQL before they built Cassandra. Mongo does scale out as well. Like everybody does. There's hyperscale for SQL. Like every database now needs a way to do this scale out architecture. We basically just started that. The
yeah,
design of the system was such that it's just going to start that way. But it's still unusual for people because they're dealing with these very small shard sizes. Versus if you're in a relational database, typically you go up to what I think it's like 4 terabytes before you would have to get into like a sharded database. Well, that's great for a single shard. Here's the thing is your access to data, once you start getting into the upper ends of these size of these things, the performance and the latency can kind of slow down. I don't care. It doesn't matter if you have like 10, 100, a million petabytes of data. The latency for accessing the data is exactly the same with Cosmos. It doesn't matter how big it is because there's the same compute. You still have compute over every piece of storage within there. It's all addressable. Basically, everything runs shallow in a database like this. It's not buried inside a 4 terabyte binary file, if you will, right? Everything is shallow is kind of the way I like to look at it. So anyway, so you've got these 20 gigabyte logical partitions. I'll talk about, there's actually a scheme we have called hierarchical partitioning. You can actually grow beyond this now where you can have a much larger partition size, if you will, but within this hierarchy that you can have within there. So, and I'll talk a little bit about that. One of the things I wanted to get to though, is when you're dealing with a scale out architecture, the usage patterns for how you store and access this data can matter a lot because each of these nodes is itself kind of a separate compute or like a separate VM, if you will. And because you have storage limitations on these things, you want to avoid kind of some of these patterns. Like if you have, let's just say usernames here, and this first one would say Andrew, and then you had the rest of the names here, you kind of want to avoid this pattern where you've got a partition strategy where everything is going under or getting stored under a single partition. Like this is bad because you're going to eventually hit that 20 gig limit. You really kind of want to spread this out. So the idea is you distribute the storage evenly across all of the logical partitions as much as you possibly can, because then you are utilizing the storage that you have across all those logical partition key values, if you will, that are within there. Same thing with the request as well. Each of these partitions, these physical partitions or even logical partitions within them, each has its own CPU and memory and IOPS. Well, if you're going to pay for that compute for all of those different nodes, you want to distribute those requests as evenly as you possibly can across them. If you don't, you end up, we call these hot partitions, right? Which is why I had that little fire thing. Right? And you get these for both storage as well as for the requests that are within there. Now, this is something that really can throw people off, particularly coming from a relational background, is they don't typically have to think about these types of things. But in a NoSQL world where you're doing with a scale out architecture like this, you absolutely have to. Like the pattern, the access patterns and the design for how you partition your data. So what is the partition key I'm going to use to access, to store this data, to route it to some logical, thus physical partition, and then retrieve it, right? Or write it and read it, if you will. Like those patterns matter. And so the choice you use in what I use as a partition key. So how am I addressing that data that is going to decide where it is physically stored? absolutely matters. And in some cases, people don't think about this, and they can end up with really kind of poor performing workloads as a
So what
result.
happened
Now,
if
well, they can get to a point where if you have a hot partition for storage, they're going to run out of storage for a logical partition, right? And they're going to get an error code back from the service that's going to say, I can't take any more data for you. From a compute point of view, they're going to see latency, or they're going to get rate limited is more likely. So they'll get a 429 back from the service that's going to say, I can't service your request. You consume too much throughput at this point for me to be able to take that request.
so is
So
that the request one like that? So yeah, maybe I have a bunch of partitions and they're all like 1 gig in size. Yeah, but one of them is like super request heavy. Like, is there a way to scale that up, or I don't know. How do I deal with
uh,
that?
I mean, we have ways you can kind of temporarily deal with this. We have this thing called burst capacity, where you
Mm.
can amortize throughput and then apply it in a short period of time. But if this is something where you have a more systemic issue in terms of the partition design, then the way out of this is essentially to design or to create a collection with a partition key that's going to have a better scale out. You just need a better partition strategy, basically, is what it comes down to. There's other ways of dealing with this, though, and let me get to that because they're actually like the things can be quite fungible in a NoSQL world in terms of how you use it as a database that can help with a lot of these things because there is no hard and fast science in some cases for how you design this stuff. It really, really comes down to the access patterns and how you design this thing. So let me kind of touch on something here, but just kind of at the end of the day, ideally what you want is you want a storage and a request pattern that's going to evenly kind of store the data and utilize the storage as evenly as possible, and then also evenly kind of route the request as much as possible, right? And that's just true for any kind of resource that you're going to use. Like you would never provision a VM that's insanely powerful and then not fully utilize it. Like you're wasting money if you're doing it. You would thus not under provision a VM and then beat it up such that you can't serve your request, right? You want to right size the thing. It's the same thing here, but you're not changing the size of the VM necessarily. It's more really how are you designing your data to reside within the resources that you've provisioned. So let me talk a little bit about like from a query access pattern. If I was going to design a container and I was going to use a username as a partition from a query pattern, really what I would love to have is I want a query where I'm going to use that partition key in the vast majority of all my queries against that container, right? So I'm going to want to use username for that, especially if I'm doing high volume queries, because that query is always going to be scoped to a single partition that will always go to one single physical partition within my container, which means that I can run multiples of this query simultaneously against all of those partitions at the very same time if I want, right? So I can get very high concurrency rates. I can do it in very high volumes when I design my data like this. Where I want to avoid is this type of thing where I have queries that I run at super high volume, but I'm not using a partition key within there, right? That is what we call a fan out. And this is fundamentally something that's not scalable because you're going to run a single query, one query, and it's going to hit every single partition in your database. And here's kind of the insidious thing here is despite what you might think, the more throughput you throw at this thing, the worse your query is going to perform. You want to know why? Because you're
Why?
going to end up with more physical nodes that have to be addressed by your query, which consumes more time, more latency, and it's just more expensive.
Where does it where does this run actually? Like, where does the gather happen when you're doing something like
It
this?
depends. So there's two modes you can run this when you're connecting or working with Cosmos. There's what we call a gateway mode, where we actually have a node that sits in the service, and the SDK will execute, distribute the query, and then do the scatter gather for that, and then bring it back to the client. We also have a direct mode, which basically the way this works is everything happens on the client side.
Mm.
So we actually distribute the query directly to the physical partitions, from the client, and then they execute all those queries in parallel, and then all the results come back, are then gathered and then sorted and then returned back on the wherever. It's not client side, like as a user, it's where the SDK is hosted. So this would be a
Yeah.
piece of middleware where you're running your app.
Yeah, I can see why that's not ideal. But yeah, it makes sense if we go back to what I was saying before about like if you were manually sharding these, if these were just a whole bunch of MySQL servers at Facebook, yeah, like this would be slow anyways. Like it's just once you physically are horizontally scaling it, like it just doesn't work to do things across, right?
Yeah. And by the way, something I want to point out as well, like there's not a whole lot of people that realize this. OpenAI runs on Cosmos, and they, when they first started, they were running on Postgres. And this has been 2+ years ago. They kind of quickly realized they were going to run into problems because of this data management, this sharding problem, right? They were growing too fast already. And so they migrated to Cosmos. They are partitioned basically on like a user ID in there. So you have a user, and then each user has one or like multiple kind of chat GPT sessions are within there. So they're here, like their query or their partition strategy is basically like user, which is a really good partition key to use, because you're not going to get massive concurrency from a single user. If you keep adding users, you just keep adding, it's a perfect kind of a scale out strategy, if you will, to do it on a per user basis. You add more users, you just keep growing compute, you keep growing storage as you grow within there. Now, in ChatGPT or in anything, could you grow to like 20 gigs of storage per user? Yeah, sure. But you can employ other techniques as well. Like we have this thing called hierarchical partitioning. So you could have something partitioned by like a user, and then you could have something underneath that as well. And that could be any value that could sit within a hierarchy. I mean, you could even have like a key where you're salting it, but it could be anything within there. I mean, we see this often with multi-tenant designs where you can have like a tenant ID, like a department ID and an employee ID, or maybe
Yeah.
company ID, department ID, employee ID. So you could have a single partition key of a company, that's your tenant. And then you could have departments within that, and then employees within departments. So you have a hierarchy there such that if I was going to run a query, I could do it by like a company ID, and then at least keep that scope to some bounded set of partitions. I'm not doing an extreme fan out like this one here, right? I'm keeping it at least scoped to something within there. So the hierarchical partitioning allows you to grow beyond kind of that 20 gig partition size by employing this hierarchy, if you will. So you can have these queries that could have data that's greater than 20 gig for that within there. So,
But then it means, that view is not going to work. That means that some queries will be expensive, right? Because some will be cross node, right? If you're doing company, department, then employee, then some cross department queries have to fan out because you're.
and here's the thing, like it's not an all or nothing type of rule, right? You generally want to apply the Pareto principle here, which is if you can get 80% or more of your queries kind of running in an impartition way, that's kind of what you want to shoot for. You just really want to hit those ones that are going to run with very high volume or very high concurrency, and just optimize for those, if you will. You're always going to have kind of these outliers of things that are just going to kind of run. That's just kind of the way software design is, right?
Yeah.
You can't solve for every single problem. And just hit the major ones, and then, and then you should be fine. At least this is what we find with customers. I wanted to kind of cover on another couple of things that we see a lot of confusion around this, like these things we call request units. It's an RU, if you will. When you provision throughput or you provision a Cosmos container, you don't provision storage, you provision what we call throughput, right? And as I mentioned earlier, if I kind of showed you earlier here, so we have these physical and logical partitions. I showed you the max size is 20 gig for a logical partition. You can't see it here because my name's over it. These physical partitions, this max size is 50 gig, but the max throughput you get is 10,000 RU. So when you create a collection within Cosmos, you don't provision storage, you provision throughput. You provision RU within there. So when you provision a container and you give it 10,000 RU, we give you, you actually get more than one physical partition. We'll give you two. but you get 10,000 RU and it's spread over 2 physical partitions in there. But basically, kind of for simplicity's sake, 10,000 RU equals a physical partition. So again, you now need to understand what is an RU, right? Because we're not dealing with CPU, memory, and IOPS. You're dealing with an abstraction layer here. And the idea is that you don't want to think about CPU, memory, and IOPS. You're trying to deal with a you're using a fully managed service where you don't have to think about that stuff. You just think about the partitioning key that you're going to use and then focus on your app, basically. And then there's some other stuff as well. But for the purposes here, it's fully managed, so we're trying to keep it simple. So what is an RU? Well, it's essentially this abstraction for this memory, CPU, and IOPS that I talked about here, right? It's basically a proxy for compute. And you consume RU depending on what you're doing. You're doing a read, an insert, an update, a query, whatever. Reads, typically for like a kilobyte of data, is going to be 1 RU no matter what, always. An insert or an update or a delete, generally around 10 RU for unindexed writes, goes greater. The greater the size of the document, once you go above a kilobyte of data, it starts to grow, and it'll grow in a more linear fashion. You add indexing, adds a little bit more in there. But the rule of thumb is, 1 RU equals a kilobyte read, 10 RU for a write for about a kilobyte of data. Now, here's the thing about RU, which is Cosmos is a resource governed service. So you get RU and it's provisioned or allocated to you on a per second basis. So when I have 10,000 RU, I provision for a collection, I get 10,000 RU per second within there. So what does that mean? This is fundamentally different also from how kind of a VM would work, or like a SQL or whatever, where you basically get your own VM, you can do whatever you want to it. But that's not the case. Cosmos is a multi-tenant service. So it's resource governed. So when you get throughput and all this, you get it allocated to you on a per second basis within there. The reason I bring this up is there's a key concept in here, which is if you have throughput and it's provisioned to you or allocated to you on a 1 second basis, things like batching data or doing things like batch jobs gets really, really super expensive. I'll give you an example. So if I have like a batch job and I'm trying to process 100,000 documents and they're about a kilobyte size.
Yeah.
If I'm doing that and that's going to cost me, and I want to do it in 1 second, if I'm going to insert those at 10 RU per insert, that's a million RU, right? So if I want to do all 100,000 of those documents and insert them, I need 1 million RU to do it. And that's going to cost me about $80 an hour for that 1 million RU. Now, what if I amortize that? What if I slow that down, right? If I do that over 10 seconds, that 100,000 documents, I only need 100,000 RU to do it, right?
Mm-hmm.
That's only $8 an hour. What if I do it over a minute? So I'm going to amortize that over 60 seconds. Well, I only need 17,000 RU to do that. That's only $1 and change to do that. What if I amortize it over an entire month? So I take that 1 million documents or 100,000 documents, and then I essentially just stream it in there. Well, I only need 4 RU to do that, basically. So I've amortized it over an entire month. It's 720 hours. So I don't know how many seconds that is, but it's a lot, right? That's going to, it's functionally, I can do it for next to nothing. I mean, basically what the minimum throughput is in there. So this is a key thing that I try to talk to customers about is if you're processing data, try to stream that data as much as you possibly can. Because if you can amortize the cost of that compute, the cost of that throughput over time, then your marginal cost is basically nothing, right? It's whatever the only throughput you care about is how much throughput you need on your reads, right? Throw your queries in there. You don't have to worry about how much it's going to cost for you over and above that because you're compressing a bunch of data operations in a small period of time.
So
now,
are you saying like we do it like as needed, like instead of doing a batch job, then
is stream it? I mean, the technical term for this is queue-based load leveling, right? Like throw it into a queue
and just slowly feed items
and feed it.
Yeah. Okay.
You can use an event grid or an event bus or a service bus or whatever queue, and then provision some compute to read it, and then just let it process that data as it can. And you can speed or slow down the thing that reads the data and processes it in, and you can dial it up or down depending on what you need. And you can build systems that can monitor this stuff. Like, okay, am I consuming too much throughput? I'll slow that down. Or I've got some extra throughput, I can speed it up in there. But the whole idea is you don't have to get that complex. If you just literally just stream data as you need, rather than batching it, rather than holding on to it and then blasting it all at once, you can typically save yourself a bunch of money because you don't have to provision a bunch of compute for a temporary period of time. You can just use whatever you've got that's just sitting around.
It feels to me like it follows from that. Like, say I was going to do some sort of data migration, like I need to change a document. Like my relational database thoughts are to run some sort of migration script, but instead you could do it like ad hoc. Like as I read this document, I'll change the format and write it back down just like lazily instead of like a big batch migration or something.
Yeah. And we actually have a mechanism that can help folks with that. And I'll talk about that in just a second. But kind of one of the things I wanted to mention before I talk about that is you can actually optimize your partition strategy based upon kind of the type of workload you have. Like it kind of goes back to this earlier thought of like these hot partitions. Like if I've got a write heavy workload, let's say I've got like a device telemetry workload, there's good examples for how you can have a good partition strategy for that. Like a device ID would be good, right? Like devices tend to emit data at kind of the same rate. So if I just have device ID as my partition key, great, then I can scale out and likely I'm going to fully utilize or saturate all those partitions with all the devices based upon the device ID. Same with the user ID, right? Like, and it's kind of less than for users. I mean, it's even more spotty in that sense, but it can at least scale out in that sense. Some terrible examples I've seen from a partitioning strategy for write heavy workloads are things like date. Like date's always a terrible partition for a write heavy workload because you're always going to have a hot partition on the current date. Like nearly always you're going to read or write data and in the where clause or in the insert, it's always going to be today in there, right? So that's bad from a partition strategy because the data is always focused on a single physical partition that is keyed for that date. Other ones that are kind of just obvious, but maybe not, are state or zip codes. Like some zip codes have more people than others. Some states have more people than others. Same with cities. Another terrible one that I see, particularly from relational designs that are trying to migrate over, are things like auto increment integers. Data in Cosmos, the partition key is hashed. So if you use an auto increment as a partition key, the hash on that thing is not going to make a whole heck of a lot of difference, right? Like you do a hash on a 1 versus a 2. First of all, you don't have enough, there's not enough characters to make an effective hash on a 1 versus a 2 or 1,000 or 2,000, whatever it is. You need a significant or a sufficient amount of text to generate the hash so that we can create different hash values for that thing for where we store the data. But auto increment, just not good as a good strategy for that. On the read heavy side, it's the thing I showed earlier, right? Like have a where clause that is going to have a single that's going to use one of the partition key and the filter predicate there, so they could get sent to there. Now, to kind of the earlier point on streaming data, what if you have mixed workloads? Like this is not uncommon at all. Like I have a workload that is both write heavy and read heavy. And in fact, this is common in device telemetry scenarios where I'm ingesting huge volumes of data from like a bunch of thermostats, but then I'm also creating dashboards to read that data in near real time. Like, how do I deal with that sort of thing? And the mechanism we tell customers to use is to use this thing called change feed. And that's basically like a CDC or a change data capture feature in there. And how it works is you create this little app and it's got a delegate in there that's monitoring a collection. And then as new data gets written to it, it fires the delegate and then you go and react to that within your code to do something here. Now, in this case, I've got this device telemetry container here that's provisioned by device ID. As I get new readings into there, my change feed app fires and then I do something with it. And in this case here, I'm implementing a materialized view pattern, right? So I'm going to write it to 2 other containers, one maybe to use to serve queries on device telemetry for buildings. Like maybe I want to get the temperature for a building, or maybe I want to get it by a tenant. It doesn't really matter. Whatever it is, you want to write that data into another container with a partition key that then gets used by some query and can then answer queries or serve queries and do it in a single partition fashion rather than having to fan out across a bunch of device ID within there. So this is functionally streaming data in there. So I write data into one thing, and then you pick it up using change feed, and then it streams it into something else. And in fact, this materialized view pattern is actually a very common use case for Cosmos, regardless of whether or not you need to build materialized views, because a lot of customers will use Cosmos to build event-driven applications because of this change feed within here, and because you can ingest enormous amounts of data and do it in a very efficient way, and then react to it, whether it's building shopping cart applications or device telemetry or any credit card payment processing, anything where you've got massive volumes of data that you need to be able to scale up and handle, and then be able to drive events to do it through to do something like this.
So it's kind of like a Kafka type approach when you're doing that.
It's fundamentally data movement. That's right. Yeah. In fact, we have great connectors for Kafka and Confluent as well.
Very
So
cool.
it's very common to use those two technologies together. Cool. I wanted to talk a little bit about replication if you got some time.
Yeah, let's keep going.
Okay. So this is another kind of area that customers who use Cosmos tend to use or choose us is because we're a distributed database, right? And we're distributed in two ways. We're distributed geographically. So you can provision a Cosmos account and then replicate it into any region in Azure. And in fact, you can replicate it into every region of Azure if you want. We also replicate within region as well for additional availability. So let me cover off on some concepts here. I think for most folks working in a distributed systems world, these three things are very common when you're building apps that have to work over distributed environments, as this consistency, latency, and availability. Because in the distributed systems world, these are the trade-offs that you are facing when you're working with apps that have to work in this sort of way. Now, why would you build an app in a distributed world like this? Why would you geographically distribute it or work in a distributed systems or build and deploy apps in a distributed system? And usually it's because you're trying to increase the durability and also have a better recovery time. And there's kind of two main metrics around that, which businesses will tend to define, which is RPO and RTO. And RPO, of course, is, how much data loss can I tolerate if something really bad happens? And then RTO is once that bad thing happens, how much availability loss can I suffer for my business here? So this graphic here kind of perfectly illustrates kind of where these two values kind of come together around kind of a bad incident that happens, which is something goes down, something bad happens. These are the two things that I have to deal with here. Worth pointing out that in nearly every situation, it's impossible to get an RPO of 0 and an RTO of 0. You can get really close. And I've seen some companies get extremely, really close, like, less than a second for this type of thing. But I will say this, that the amount of investment and engineering involved with driving this thing to near zero increases exponentially the lower you get. Cosmos gives a lot of goodness around this and does it in a very, I think, a low cost fashion and in an easy and approachable fashion. And so I kind of wanted to talk about kind of what we do around this. So kind of a primer for folks that aren't familiar, this thing called CAP theorem. This has been around for like a decade or more now. But basically, in a distributed world, you've got these choices. You have availability and consistency. So if you lose data between, say, a master and a replica in here, you can choose availability for that application, which is, this. So I lose I lose connection between my master and my replica here. That's fine, right? So if I write new data in here, I'm choosing availability over consistency of that data. So I'm just going to continue serving reads from my replica. I don't care. Of course, if I choose consistency over that, that data and something happens, I'm not going to accept any more writes basically in there. So that's kind of the trade-off in a CAP world, is that consistency and availability. And then of course we have PAC-LC, which is in a world where you don't have basically partition between your master and a replica. You still have another trade-off, which is this latency and consistency trade-off, right? So, sorry, kind of going too fast here. So you can choose latency between those things, or you can choose consistency for that data that's replicated over some period of, or some distance between the two. So anyway, just a primer. There's lots of stuff written on CAP and PAC-LC. So if those are concepts that are new to folks, definitely go read up on them. I wanted to spend a little bit of time talking about consistency models. So in a world where we're distributing data across vast distances, these essentially provide kind of a contract, if you will, for dialing in RPO on data that's replicated. And we have 5 levels of these consistency models within here. And I'll kind of go through each of them. Like the first one here, strong. This is probably the most familiar to folks. But fundamentally what this means is when you have data that's being replicated to some other region within Azure. So this is, could be hundreds of thousands of miles or tens of thousands of miles away. The contract here is that your data is always consistent, perfectly 100% consistent. And we will not accept writes unless we can replicate it and commit it into every other region within Azure. And then that has to be committed fully and then act back to the region where it's written before it's act back to the user. So the behavior here is data is 100% consistent all the time. However, this is done in a synchronous fashion. So when I write a piece of data into, say, some region, I'm going to wait for that to come back before I can move on and do something else in there. So you're going to get a higher level of latency when you write data in there because of this consistency guarantee for your strong data. Now we have another level that's a little bit weaker. This is called bounded staleness. And kind of as the name implies, there's a staleness window to it, but it's bounded by some amount. And that's governed by either some period of time, and this is about 300 seconds as a minimum within there, but it can grow much higher as well for multi-region, or it's some number of writes. And I think the minimum number of writes is like 100,000 or so, or maybe 10,000 within there. And beyond those staleness windows, we actually will stop writes. We won't accept writes within there. And for some people, this is actually something they want within there. We don't see a whole lot of customers using bounded staleness as a consistency contract, but in some scenarios, customers do want this type of guarantee within there where they want to make sure that they have a staleness window, or they want to be asynchronous because this is an asynchronous consistency model, but they want to keep that or define it to some staleness window, if you will, within there. And then let me talk about the others. So we have another in here. I'll take session last because that's a kind of a unique one. Consistent prefix is another consistency model, weaker still. And the behavior of that is that you have data that's in order, but it's for a specific prefix within that. So that basically, what that means is that within a partition, it's always going to be within a specific, that it'll always be within order, within a specific partition within there. And then there's eventual, which is exactly what the name implies. There's no guaranteed order, no matter what within there. Now, let me talk about session. Session is actually the default consistency model we use. And it's completely unique from these others in that these other consistency models are data centric. Session consistency is, in fact, a client-based consistency model. And the way it works is it uses an LSN, right? So a log sequence number. So when you write data to Cosmos, it generates a log sequence number for the partition that it goes on to. Now, when that write happens, the client will return that LSN, and then you can send that back to your ultimate client that actually wrote the data. The way you the way you implement session-based consistency is you go and you write some data into Cosmos, and then it brings back the ACK on that, right? And then the log sequence number. And then if you go and you issue another read on that data, you pass that log sequence number, that session token, we call it. And then we will always guarantee that you will be able to read that write that you've had in there. This is how we guarantee. It's basically, so the consistency contract is read your own writes. Not strong. Some people will say that it's like strong. That's not true. It's read your own writes. So you will always get the latest data that you wrote. So the mental model to use here is if I'm using a shopping cart and I write and I had a product within there, and then let's just say I'm using some kind of round robin for my middle tier within there. I don't need to have, I can use a round robin. I don't need sticky sessions or anything like that. It's going to maintain state for that. I can go back to any middle tier server in there, pass that session token, and then it'll do the read. And then I will get back the cart and with the latest products that I added in the cart in there because I'm using that token, that LSN. So that's how a session token and how the consistency model or a session consistency model work. And it's unique compared to these other ones here. And it's our default. And it's our default for a good reason, which is when people think about the data that they want, it's usually the read your own rights is the pattern to go for it, right? It's not strong. It's read your own right. I want to see the data in there last. I don't care about anybody else's, but that's what strong is. Is strong is the whole thing is completely consistent 100% of the time and in every single region. That's not necessarily what you need when you're writing applications. It's typically that read your own right pattern they want.
That's cool. So
Yeah.
does it wait? Like what happens when it gets that sequence key? Does it wait if it
So
doesn't have that yet?
great question. So the way it works is when you read data from here, you have within a region, you have this thing called a replica set. When you write data within there, you write to what we call this local majority within here. And that basically is going to be 3 of these 4 replicas within a replica set. So this is your data. And within each of these, you would have you would have partitions as well. So just to give you kind of a mental model as to what you're looking at here, within each of these replicas, you have all the partitions. So if I have 2 partitions, I've now got 8 basically with all the replicas because we quadruple your data every single time you write it within here. So when I write data, I'm writing it to 3 separate replicas within my account, within that region within there. When I read it, I'm reading it. When I do either a session, a consistent prefix, or an eventual, I'm only reading from a single replica within there. When I'm using a session token, what will happen is we pass that session token back to that replica. Let's just say I wrote to these 3 right here.
Yeah.
And I do a session read from this one. Let's just assume that this replica did not get hydrated yet with the latest write. What will happen is the service will retry it on the leader node here or on another follower within there to look for that LSN. So it will always get, no matter what, your latest data within there, even if you issue a read right back to it before it's had a chance to replicate to that last one there, it will look for that LSN and make sure that it gets it.
So what does that? Some front end on top of this, I guess.
Yeah. So this is basically it's at a gateway level within the service when you're doing the reads within there.
That's super
It will
cool.
do it. Now, let me show you this. So strong and bounded staleness do what we call a local minority read. So if you're curious how we guarantee strong consistency, it's basically using the same LSNs. The way it works though is when we do a strong or a bounded session read, we're actually reading from 2 replicas in there. And what we do is we compare the LSN between them for that data. If they match, then we know it is guaranteed to be the latest data. And the reason is because we wrote to 3 of them in there. If it doesn't match, let's just assume it's this right here. We will always pick the higher one because that is always going to be the latest data within there. And that's how we guarantee strong consistency within that. It's of course not going to be just within the region. Of course, it's going to be global because if you read here on the table, when you write, it's not just writing to these 3 within a region. It's writing to those 3 in every region that you're configured for within here.
So the write on strong consistency has to act from everyone, but the read just has to pull from one.
That's right. Or a local minority, which is 2 replica. And one of the reasons I point this out is the cost of a read using strong or bounded staleness is double what it is for single replica or for basically doing a single replica or a weak read. So this is something that usually people don't fully understand is that those are more costly because you're doing a 2 replica read in there to get that guarantee. And then also another key thing as well is consistency is on the read path. It's not a write thing, right? This is another reason why you cannot have, when you define consistency within Cosmos, you do it at an account level. You can change the consistency level on a per request basis, but you can only weaken it. You can't make it stronger. So this is another thing people should be aware of as well. And typically the pattern we see, customers want to create a dashboard for something. It doesn't make sense to pay to do reads for a dashboard typically you don't need perfectly consistent data for a dashboard. So they will set up a secondary SDK session and then have a reduced level of consistency within there. But again, it's a very niche-y use case where you see this type of thing. Most everybody, which is again why we use that as a default, is using session consistency because this is exactly the pattern they want. But in some cases, people do need RPO 0. They do want strong consistency, and they're willing to take the hit for the availability for one, but also the latency, because you have to replicate and commit that data globally in there.
Yeah, that's super interesting. Yeah, there's some tricky trade-offs in there where
And it's all trade-offs,
yeah,
right? It's again, you're building distributed systems. Everything's a trade-off in there. You have to give up something for something else. It seems like, I mean, you can get really close on stuff. And like I said, I've seen customers that have done some amazing engineering work on building systems that were highly resilient, and had near zero RPO, near zero data loss, and near zero availability loss. But the engineering that goes into this sort of thing, like I said, can get very expensive very quickly and very complex very quickly. And we try to provide this type of thing in a fully managed service, right? So you can, select the consistency level you want based upon what your needs are from an RPO or an RTO perspective. Because if you're going to have an RPO 0, you've got to give up availability and latency is something you're going to have to give up, right? But if RTO is something that you care about, then you're going to need to pick a consistency level that's weaker in there as well. The other thing I didn't talk about as well is, and this is another unique factor for Cosmos, is we run active-active. Like you can have multiple regions configured to accept writes, and you can have them all set to accept writes. You can run an active passive if you want, and that's kind of typical if you see like a multi-region setup in a relational database. It's very uncommon to see relational databases configured to run active-active, where you can write into completely different instances of it, and then they replicate and then merge the changes in there. But you can with Cosmos; it's built to do that, and then we have different mechanisms for how you handle conflicts within there as well, and that's how customers can choose how they want to manage the conflicts within there. We have easy, like the last writer wins, that's a simple one, but you can build very complex apps or services on top of there to merge all of your conflicts if you want as well. So
yeah, it's very cool. Before we started recording, you were saying how, some of the ways that Cosmos works, like they reflect the implementation, right? And the implementation reflects requirements, but also the physical world of like distributing data. And I think that's very apparent. Like the decisions that people have to make. I mean, they'd have to make anyways, right? If you get to a certain size, no matter your database source, you're going to need to partition, right?
and this
You're gonna
exactly, and this is why the service the way it is customers we're trying to solve the problem that customers are trying to solve, right? And we see this every day from the customers that use us is we're going to pick you because you've already fixed the problem that we've got. I mean, whether it's OpenAI in terms of being able to just have basically unlimited scalability and storage, or nearly every service in Azure is running on Cosmos. And there is an enormous distributed system is running a cloud globally, and nearly every service in Azure is running on Cosmos. And if you ask the teams why, they're like, because you've solved kind of the hardest problems for us, which is how to manage distributed data. And, and that's it, right? Like we want it fast, and we want it reliable and available and safe. And so that's the thing that's our North Star for why we are the way we are.
Yeah. Well, thanks for sharing all this, Mark. Yeah, somebody reached out to me from Microsoft Teams before, and they were like, "Yeah, we use Cosmos, and it's awesome." Yeah, but so thanks for sharing. We'll put the links to like your Learn Cosmos DB and stuff in the description.
Yeah.
Yeah. Oh, sorry. Go ahead.
No. I threw a couple of links up there. People are curious if you wanted to show a slide. I've got a slide to our gallery of lots of samples of stuff. If you want to see how people are using Cosmos, there's lots of samples there. We have a YouTube channel as well. If you want to come and see videos, I run a show similar to yours. I don't think I do as many shows as you do, But we do have we have episodes of our show, and I have guests on and stuff as well. And I've actually had folks from Pulumi on in the past as well. So
Yeah, we got to
you guys
do
are
a
good friends.
crossover. I think it's been talked about, but I would like to come on your show. We'll show how to use Pulumi to set up things, set up Cosmos DB, set up Azure, and yeah, thanks for coming here. And I want to mention, yeah, if you're watching this far and you're on Azure, you should check out Pulumi Insights because it has support for Azure, and sometimes it's really useful to see actually everything that's in your cloud account. I mean, sometimes we love to live in a world where everything's set up with infrastructure as code, especially here at Pulumi, but sometimes there's things that aren't. And yeah, we have this new product, Insights, that lets you see everything, imports all your resources. And I found it super useful because I found when I was testing it out that there was this like Kubernetes cluster that somebody had set up in Azure and forgot about, which is not cheap. Yeah, so check that out, everybody. And yeah, check out Mark's resources. And thanks for coming here, Mark. Thank you very much.
Yeah, thanks for Adam for having me. Great to be on.